Hi, this is Bill, and I'm going to talk about why I must not be even all that good at my work. But anyway, this story is about the drama that's happening on the EASY experiment, which is the Electrojet Zeeman Imaging Explorer. Okay, the EASY experiment is designed to measure the magnetic field of the Earth, and what they want to do is they want to look for perturbations and put it into these geomagnetic models to, I guess, model currents and electrojets and things like that. And they launched this back in March. Our instrument, which is the microwave limb sounder, actually measures the same signals, but not as comprehensively. That's probably the best way to do it. So we only get like part of the information, which in this case is the total magnetic field. We can't really get the direction all the time, although we actually can if we turn on the two radiometers that measure opposite polarizations, but normally we're not operating that way, whereas EASY actually gets those polarizations and plus circularly polarized as well, so it presumably can pull out the whole vector. So anyway, here's the drama. Because last week, I guess they were threatened by, I guess, NASA headquarters or someone up there said to produce, I guess, Zeeman electrojet maps off this experiment, or your funding is over. So yeah, can I tell you, for 2 seconds I wasn't buying this, but I guess the two people that are getting funded were pretty freaked out by it. So they've been working day and night, I guess, to try to do retrievals and things like that. So anyway, I was talking to them about that, and I said, maybe we should see what MLS could do, because I've got an operational retrieval all set up to roll on this if somebody wants me to do it. So they gave me this day, May 3rd of this year. They said, there was a lot of this anomalous magnetic activity going on over Canada in particular. So so I went ahead and just cranked down a retrieval, first over Canada, which seemed to be the area of interest, but my data didn't show anything particularly interesting. So anyway, let's go to the figures and charts. Oh, by the way, they didn't get their funding cut. I guess someone at Johns Hopkins University Applied Physics Lab was able to show them some data, I guess convince the manager that, they can produce results, and they need more time. So, I was right. Okay, our instrument measures a microwave emission from the oxygen line. And because it is a ferromagnetic molecule, ferro meaning it's basically sensitive to magnetism, you get a split here. And it's the separation between that split actually is the magnetic field measurement. So that's what we need to model or fit is the separation of those peaks. So that's basically how the measurement works. Okay, so here's a map of differences between what we retrieve in something called an IGRF model, which is the model of the Earth's magnetic field in a nominal quiescent state. And so what we show here are the differences. And of course I said, look over Canada. In northern Canada, all this action was supposed to happen. So I focused here. And I said, I don't see much of anything happening here. So I said, screw it, let's just retrieve the whole entire day. So this is the entire day mapped, where we've got good data. And of course, there seems to be some activity over here, possibly. Okay, so anyway, so here's the map of all the differences with the RGRF model. And boy, what was I told misleading information about this, but so anyway, start digging into this, and this is what I find. Okay, I'm just showing this because it's a pretty picture. This panel up here shows the signals that we measure, and we measure like 3,500 profiles in a day, from 80 south to 80 north. And so the values range from 120 to about 225K. And then the bottom here shows you how well we're modeling and fitting those signals. And I think is really good. We're doing awesome with this. I mean, the noise on these radians is about 15K, so we're getting it within noise. And it even got a little bit better toward the end of the mission. That's because I did a tuning thing on my retrieval to let it run for more iterations, so give it better opportunity to converge when it didn't converge. So anyway, looks pretty. Okay, here's a map of the field we retrieve and then the differences. So notice that the values of the Earth's magnetic field range from about 20,000 nanotesla to about 65,000 nanotesla. And the differences are typically within about plus or minus 1,000 nanotesla. The black spots here are where the retrieval did not converge properly, so that data has been nixed. So yeah, just looking at this, you can see that we're getting agreement at the maybe the 1,000 nanotesla level or better. And the next one I'm going to show you is going to be the real crux of the issue here. So, okay, the top panel is the same one I showed before, but the bottom of it, I've shown it in percent. And as you can see, we're fitting this field within, say 3%, plus minus 3%, which actually is pretty awesome, really, because I don't know if the calibration of the radiometer of the instrument is that good. I showed this to our instrument guy, the guy who designs the instrument stuff, and yeah, he was very impressed. He said, "Wow, this looks good. The instrument is working really well." So all that sounds like really good news. Until I tell you the next part of this is that the type of signals they're trying to find in this field range from about like maybe 100 or 200 nanotesla. So we're actually talking weight like sub 1%, maybe 0.5% or better. And that's going to be the challenge for us and for them. And our instrument calibration is just not at that level. So yeah, this is going to be a problem. Yeah, let me show you what this looks like in signal space, just for curiosity. Okay, here's one retrieval that I did not let temperature go below 150K, so it did not converge as well. And so the point to note that here's the field that it fitted. Now, actually, this was a challenging situation because the lines are merging together because it's near the equator and the field is low, but nevertheless, you get 0.242 Gauss, and here's the chi-square 1.78. So and you say, yeah, it looked like it fit pretty well. I mean, here's the model fit. Okay, when I fixed the low temperature bound to let it go down to 100K, which it needed to do. Again, the measurements are exactly the same at the top. The residual at the bottom looks pretty much the same as the previous one, but notice the field dropped 1,000 nanotesla, and the chi-squared is now 0.67, which is a better fit. So, yeah, I'm at this point looking at this. You can't tell that one's better than the other, really, but it's a 1,000 nanotesla difference. And here we're looking to try to pull out a 200 nanotesla effect. So this is going to be a challenge. Boy, I tell you, I was misled on a lot of stuff here. So anyway, here's some results from something they call SuperMag. It's an operational magnetic field and electrojet modeling facility that is at the Johns Hopkins University Applied Physics Lab. And so they can produce these maps here, and all these black vectors are, I guess they would be, I think, various perturbation magnetic field indices off of a nominal, say, IGRF model. And what they do is they simulate all these ground stations, which are these red vectors you see here, and they put it in their model, and it can produce some, I guess a filled out field. And what the goal of EASY is to try to fill out all these gaps in here that are not covered by these ground stations. To help to do this better. I guess that's the best way to do it. So, and they have these indices here called S of U and S of mine. I don't entirely understand it. And by the way, people I'm working with don't understand either, because they showed this to me. They say it's a nanotesla. This makes it look like, oh yeah, we should see this big 1,000 nanotesla event, if you will. Then it goes quiet, and then there's almost another 1,000 nanotesla event. Now, the EASY satellite itself actually has 4 measurement tracks, and they have 3 satellites. So that's the blue, the yellow, green, and red. And this here shows the times that those are coincident with this time series. Now, the thing to realize is that this index is some global, probably high latitude. It's not specific to any area, and I know this because you see that there are 15 lines here, and that's how many times the satellite goes around the Earth. And so anyway, this is not coincident with any station. It's some aggregation of measurements of all stations, and this is what pops out of their model. And so anyway, so this is what they are, and I guess they're saying that, because there's some big events over in Canada, and also later in the day you see big events happening over Scandinavia. They were saying that, oh yeah, you should see these big events. So, yeah, so that's what it is. Oh, I hate geomagnetic coordinates. That's what this looks like, a geomagnetic coordinates. I mean, yeah, hate those. So anyway, this is kind of cool. I went to the John Hopkins website called SuperMag, and with a lot of tedium, did download a bunch of station data, and went ahead and matched up coincidences with the MLS and made what we call a scatter plot. So the stations are on the x-axis and MLS is on the y-axis. These are in nanotesla units. And the coincidence criterion is 15 minutes plus or minus 5 degrees longitude plus or minus 2 degrees latitude. And these are stations that are 50 degrees north or more polar, higher latitudes. So the black bullets are the MLS measurements. These little crosses you see here is the IGRF model. And so you can see correlation actually is really good, in the bulk sense of the word. And the fact that the MLS is measuring lower than the stations makes sense. Michael at my group kind of explained this. He said that's because MLS is seeing the magnetic field about 80, 90 kilometers above the surface of the Earth, whereas the stations are right at the ground, so the field will drop off as you go higher in altitude. So this offset from one is actually a real physical thing. It's not an instrument problem or something. So again, the question is whether we can measure these 200 nanotesla variations in there, but certainly we're measuring the magnetic field. So this is kind of a cool plot. This is what we're really after, is the perturbations or changes relative to the modeled Earth's magnetic field from the IGRF model. So what is plotted here is like the previous plot, but it's a scatter plot with the IGRF subtracted from the MLS measurements and the IGRF at the station subtracted off the ground station. So the vertical bars up here are the uncertainties on the MLS measurements, and the ground station has an uncertainty of probably less than 1 nanotesla, so it's basically negligible. And yeah, the dashed line, a bit hard to see, it's a 1-to-1 line. That'd be perfect agreement. The solid line is the actual linear fit. The correlation is 0.31, which is actually not super great, but there is a correlation. So MLS is able to pull out these small perturbations on the background magnetic field. And this is what they're looking for as far as modeling the electrojets and currents in the atmosphere. And yeah, so that's what they want easy to do. So, and actually one thing, I was a little depressed when I saw this because I was hoping to see a better correlation, but then after thinking about this actually would be useful, even in its kind of just kind of out the gate state, because these models actually do use elements of AI to be able to statistically use this data in the most optimal way. There's clearly a correlation here, so MLS would be adding information. Given that MLS measures like 3,500 measurements at all different locations and times over the world, whereas the stations, there's about 500 stations across the world, but there's lots of regions of the world that are not measured, like specifically over oceans and lightly populated continents. So yeah, they could use this for a simulation. And then one thing I do know is that let's say the calibration of MLS is probably not better than 2 or 3%, but looking at the data, I bet I can prove this by a factor of 2, just by more analysis, because I'm pretty sure there's something called a standing wave artifact in the data that will distort things a bit. And yeah, again, given work, I probably could take this out. I mean, it'd take quite a bit of work. And I think I could probably improve this correlation by a factor of 2 or maybe even more. So that's where we are. And see, one way I know how to tune this out is that we also measure wind, and there's a bias in there, and it really shouldn't be in there. So what you do is you adjust the parameters you need to do to take out or tune out the wind bias, and then you see what it does on the thing you're interested in here, the magnetic field. And I'm really confident that if I figured this out, it would improve this a lot. I've done this with other things in our instruments with success, so I have experience in this, so I think it would really work. Okay, the goal is to assimilate these magnetic field measurements into a model, so they can make maps like this. We got the vectors all over the world based on a few measurements you get from the ground. And of course the satellite's going to fill this in so much more, which is what they want to do. So yeah, anyway, I showed these results to our instrument scientist, and he was actually really happy and impressed that it was working this well, because again, we're trying to pull out a sub% effect on top of a big measurement, and the instrument really probably wasn't really designed for that. It's designed for composition measurements where 10% is usually considered, you're really happy with that. Temperature is a challenge for us, again, at the sub 1% level. I mean, we can measure temperature within, maybe 2K, 1 or 2K. But, yeah, but as I say, off the signal, that's again a 1%, that's 1% or better type measurement we're going for, and we do have artifacts. So again, this is not surprising. I think I know tricks you can do with our data to, as I say, to get this a lot better, because I have a familiarity with the instrument. I would go for this. on the easy side of things, they apparently said that, I think I was told by one of the guys that's getting paid by this, that they did their own retrieval, and they were off by 4,000 nanotesla. So he asked me, he said, what did you use for your constraint? And I said, about 50,000 nanotesla, which is basically no constraint. Because they were trying to measure something that's a few hundred nanotesla. So they were off by 4,000 nanotests. And so what they did was they tightened down the constraint a lot, so that way it would come out closer to the IGRF field. And I guess they got better results doing that, probably not surprisingly. And then I guess they were able to sell it to their project management that they're doing a good job. So yeah. As I say, this is just what I've shown here is what I call an out the gate. Let's see what we could do retrieval, and then it looks like it's working pretty well, at least with the MLS data. And hey, I wish I could be working on easy. I'd like to try my retrieval on their data, but they haven't given that to me, and I'm not getting funded. I guess I'm not good enough to get funded by easy. So I guess that's where that is, and it kind of reflects my whole experience in life. I mean, like with YouTube, I just passed 500 subscribers, which is pretty cool. Although it's taken me 2 years. It's the same at my work. I guess no one is really that impressed with what I could do, and yeah, it's a challenge for me. So that's I guess all I have for you today. And if you like this video, please like and subscribe. It helps me with my low self-esteem. And anyway, happy 4th of July, everybody. Bye-bye.